Okay, this is an attempt to cram a whole first semester of AP high school physics into 30 minutes, let's say, video. Ready, set, go. Okay, so we start with the big five motion equations: distance, velocity, and acceleration. Okay, the five basic velocity equations. The most basic one is distance equals velocity times time. This makes sense. Velocity is meters per second, time is seconds. Seconds cancel out, and we're left with distance, meters, for example. Now, a little bit more complicated, but the same basic concept. Let's say you have constant acceleration. Then if you take v1 and add it to v2 and divide it by 2, that's the average velocity. And if you multiply the average velocity times time, once again, you get the distance. Same thing, except with a constant acceleration. Now, we'll get a little more complicated. The ending velocity equals the start velocity plus constant acceleration times time. Now for this equation, you don't need to know the distance to be able to figure things out. And if it starts from 0 and it starts accelerating, then v1 equals 0 and it cancels out. So there's all kinds of little quirks like that that make this easier, sometimes harder. Here's the distance equation. The ending distance is equal to the starting distance plus the starting velocity times time plus 1/2 the constant acceleration times time squared. You don't need to know the end velocity to use this equation. Now, of course, if it starts at the starting line and the d1 equals 0, and if it starts at a 0 velocity and v1 equals 0, then a bunch of stuff cancels out, and you're just left with the distance equals 1/2 at squared. Of course, you have to have constant acceleration for these to work. Finally, and this is the one that I always have a hard time remembering, the ending velocity squared equals the starting velocity squared plus 2 times the acceleration times the distance. Let's say you don't know the time, but you want to solve for one of these other things. Ta-da! Here's an equation just for you. So those are the big five velocity equations. Okay, here's some special kinds of situations. Free fall. You have something and you drop it off the Leaning Tower of Pisa. This simplifies the velocity equation. So let's say you have this, but you started from velocity 1 equals 0, and then you let go. And we know what A is because A is gravity, the force of gravity, which near the surface of the Earth we say is 9.8 meters per second, 9.8 meters per second squared. So this becomes your ending velocity equals negative g, 9.8 meters per second squared, times the amount of time. So let's say you jump out of an airplane, and you fall for 10 seconds before you open your parachute. How fast will you be going when you open your parachute? Well, this is easy. It's negative 9.8 times, that's 10 seconds. Yay! Okay, or 98 miles per hour. 98 meters per second. Okay, so here's the distance formula. Let's say we start from a distance of 0, and we start from a velocity of 0. Those cancel out. A is negative g. This becomes x, the ending distance. You can figure out how far you've dropped if you do negative 1/2 gt squared. 9.8 meters per second squared times the time. There you have it. Simplified velocity equations in free fall. Another very common thing that you'll study in first semester physics is projectile motion. Here we've got two types of motion going on at the same time. You have horizontal motion, and then of course you have the vertical motion. You shoot the cannonball up in the air, it peaks and it comes down. So you have the horizontal part of the vector, and you have the vertical part of the vector. So you're going to have to do a little bit of trig. Now the horizontal part, a body in motion wants to stay in motion, so you're going to have a constant velocity. This may be counterintuitive, but trust me. The velocity on the horizontal is going to be constant. There's no acceleration. v1 is going to equal v2, and acceleration is 0 for the horizontal part of it. Now for the up and down part of it, gravity is going to be pulling at a constant acceleration, a negative acceleration, the whole time. So A, the acceleration of the y, is going to be negative g. So you're going to have to do a little trig here. Oops, sorry. You're going to have to do a little trig. So if you shoot the cannonball at velocity 0, at an angle theta from the horizontal, you have the y component of the velocity, and you have the x component of the velocity. Using a little trig, the cosine of theta is the adjacent over the hypotenuse. So to figure out what the x component of the velocity is, you're going to multiply the velocity times the cosine of theta. And to figure out what the y component of the velocity is, you're going to multiply it by the sine of theta, because the sine is the opposite over the hypotenuse. Now, so to figure this out, a lot of times you're asked questions like, how long is it in the air? And that's a question of the vertical, right? Because you know from the free fall equations, you know that velocity 2 is going to equal 0 at a certain amount of time. And so you can figure out the amount of time going up, and it's going to be the same amount of time coming back down. Once you know the total amount of time, then figuring out the distance is easy, because this is going to be constant. It's just vt. Whatever the time you figured out for the up and down, then you vt, multiply the time times the x component of the velocity. So that's projectile motion, not projector motion, although you could launch a projector up into the air, I suppose. It would go crash, probably. Okay, circular motion. Circular motion when a car curves. So when a car curves, it has the body in motion wants to stay in motion. One of the velocity wants to point tangential to the circle. We call that centrifugal motion. There's not really a centrifugal force. Basically, the body in motion wants to stay in motion. There is a centripetal acceleration, however, that is inward or radial toward the center of the circle. It accelerates inwardly. So here the equation to remember is that the radial acceleration of something in circular motion is v squared over the radius. That's the equation to remember here. V squared over the radius. Here's one, that basically breaks it down into the circular distance over time and so forth. But anyway, this is the one to know, especially for your AP exam. V squared. The radial acceleration is v squared over r. Okay, Newton's laws. Newton's 3 laws. Remember them? What are they? 1, body in motion wants to stay in motion. Body at rest wants to stay at rest. 2, F equals ma. And 3, for every action, there's an equal and opposite reaction. Newton's first law. Body in motion tends to stay in motion. Body at rest wants to stay at rest. So you get problems like this, where you have a car that's it's not falling down, it's standing still. So we know that all of the forces have to balance out. There are 3 basic forces. This is called a free body diagram. And so there's the tension force. That's what's holding it in place. There's the normal force, which is perpendicular to the inclined surface. And then you have the weight force. Weight is mass. There's a difference between mass and weight, right? Mass is the amount of mass, the stuff. Weight is the mass under the force of gravity. So if F equals ma, then the weight force is ma or mg, where g is 9.8 meters per second squared. So that's the force diagram. You've got the tension force, you've got the weight force, and then you've got the normal force, which is what keeps the car from falling into the center of the earth. We don't usually think of there being a force pushing back up on me to counteract my weight pushing down, but if there weren't a force pushing back up on me, then my weight would take me down to the center of the earth. Okay, so now the trig part of these inclined planes and the normal force is the opposite of what you might think. The key is to remember that the weight force is the hypotenuse, and so the normal force is going to be this. The cosine of this angle times the weight. I would have thought, my common sense tells me, wait a minute, isn't this the opposite? Isn't this the sine? But to find the component, you're going to use the cosine, because just remember, with inclined planes, the normal force is going to be the cosine, not what you might think it is. So we figure out that the force wanting to pull the car down is this. So we know that the force needed by the tension force to pull it up has to be this. So then the cosine of 31 is going to be the adjacent over the hypotenuse, where t is the tension force. Solve for t, and you've got the tension force needed, this, in order to keep it from sliding down. So there's a Newton's first law kind of problem. Newton's second law, again, is force equals mass times acceleration, where F is the force, A is the acceleration, and M is the mass. Or to put it in words, 1 Newton is the amount of force. Newton is the unit of force. 1 Newton is the amount of net force that gives an acceleration of 1 meter per second squared to a body with a mass of 1 kilogram. So a Newton is a kilogram meter per second squared. So Newton's second law is when the net forces on a body are not zero, and so it moves. You know, with Newton's first law, you're usually assuming that all the forces are in equilibrium and that there is no force winning out over another. But when the net forces on a body are not zero, then Newton's second law comes into place, F equals ma. So here's a problem. Let's say there's a 50 kilogram woman on an elevator that is decelerating. In other words, there's a kind of an extra force pushing up on her as the elevator slows down. So let's say this elevator is decelerating at 2 meters per second, but she's standing on a bathroom scale in the elevator. What is the scale read? In other words, what is her apparent weight? Not her real weight, but her apparent weight. So here's a free body diagram. She has the weight force, mg, those times each other, and we've told you that the acceleration is 2 meters per second squared. So her apparent weight, we take the weight of the woman. Again, remember, mass is kilograms, and then we take gravity to get the weight, 490 newtons. And then the force from deceleration is going to be those 50 kilograms times 2 meters per second squared. So her apparent weight is 590 newtons. There you have it. Okay, Newton's third law is that for every action there is an equal and opposite reaction. So if a body A exerts a force on body B, then body B exerts a force on body A. These two forces have the same magnitude but are opposite in direction. So basically, let's say you have a mosquito that hits a windshield on a car. The MA of the mosquito equals the MA of the car. But because the car has so much more mass than the mosquito does, the acceleration of the mosquito is incredibly much more than the acceleration of the shall I say deceleration of the car. This is why the mosquito goes splat. Anyway, forces always come in pairs. So we already mentioned the normal force that keeps you from falling to the center of the Earth. If two astronauts are at rest in space and one pushes on the other, then they're going to both drift apart with an equal and opposite reaction. Okay, frictional forces. So static friction force has to do with the amount. Let's say you have a carpet that's on an incline and something sitting on it. The static friction force is has to do with the amount of force you're going to have to exert to get that thing to start moving. So static friction force is the kind of friction you have to overcome to get a body to slide across a surface. It is approximately proportional to the normal force, which is the force pushing up from the ground. Or in an incline, then you have to do the tricky trig. So basically, until you get the force above the equal to, so mu, this is the static, mu is the coefficient of static friction. Mu s is the coefficient of static friction. So if you take the coefficient of static friction, which is some number they give you in a problem, multiply it by the normal force, which if it's on a flat surface is just the weight. If it's on an incline, then again you're going to do the cosine of theta times the weight, and that's going to give you the force. You're going to have to exceed that force of static friction in order to get that puppy moving. Now the kinetic friction force is once it's moving. So once it's started moving, you have a different coefficient of kinetic friction. So kinetic friction force is the kind of friction that acts when a body is already sliding. And again, it's often proportional to the normal force. So here we have a different coefficient. We have mu k is the coefficient of kinetic friction. N is again the normal force, which if you have a horizontal surface, it's just the weight, the opposite of the weight. If it's on an inclined plane, then it's the weight times the cosine of whatever the angle is. But that's the force that's going to be resisting motion. Okay, so sometimes you have to balance this force against the friction force. Okay, the dynamics of circular motion. So we already talked a little bit about, remember, just a second ago, the acceleration, the centripetal acceleration of circular motion is v squared over r. So basically, we already had this. The radial acceleration is v squared over r in circular motion. Now, yeah, there's another version of it. Oh, I'm sorry. I had tried to get this down, but it didn't do it. This should not be MAR. It should be MA rad, MA radial. All we're saying here is that if A equals v squared over r, then the inward force, the force, centripetal force, is MA, or M times v squared over r. If A is v squared over r, then MA is mv squared over r. And that's the centripetal force it's going to take to keep that thing from going off into a tangent. Okay, kinetic and potential energy. We're getting close here. There are only 10 of these slides. So kinetic energy, here's the equation. Kinetic energy equals 1/2 mv squared. Kinetic energy is the energy of motion, how much energy it has. Gravitational potential energy. That's how much potential energy does something have if I'm holding it here. Well, if work equals force times distance, which we haven't had yet in these slides, and force equals mass times acceleration, then if we take this and put it into force, we have mass times acceleration times distance, or mgh. So the potential energy of something you're holding up, that's the energy waiting to express itself, motion waiting to happen. So if you hold a rock up here, what is its potential energy? It's the mass times the gravitational force times the height that you have it up, mgh. Unit potential energy equals mgh. Okay? Now I do have sometimes I'm fitting in elastic potential energy in here. Hooke's law is something you would have already had by now. Force equals a spring constant, times the amount of stretch you've given it to it. So what is the potential energy for the spring? Just memorize it. It's 1/2 kx squared. It's kind of like 1/2 mv squared, so I don't know if that helps you remember. This has been a slight diversion that I didn't know where to slip in, so I slipped it in here. Okay, the law of conservation, and now back to our regularly scheduled kinetic and potential energy. So energy is never created or destroyed. And so what we find is that, and I may have this on a slide, is that if you start with something, let's say you're holding something up here, mgh, and you let go of it, what is its kinetic energy going to be when it hits the ground? Well, it's going to be exactly the same as the potential energy it had above the ground. So mgh is going to turn out to be 1/2 mv squared when it's about to hit the ground. So there's a conservation of energy. So if the potential energy is fully expressed into kinetic energy, then you could do the same with a pendulum. If it has a certain amount of potential energy when you're holding it up here, then by the time it hits that full speed at the bottom, or swing or whatever, it's going to be that potential energy is going to be fully expressed as 1/2 mv squared. Okay, we're getting close to the end. Work and power. So if a force pushes straight on, then basically work, the amount of work done, is the force times the distance. That makes sense. How much work did you do to get that chair across the room? Well, I pushed at this force for this distance. So force times distance gives you the work. No problem. Now you may have to do some trig, unfortunately, if you're pushing on an incline, if you're pushing at an angle and so forth. So just use your trig. The work energy theorem basically says that work is the change in kinetic energy. So if you had a certain amount of kinetic energy beforehand, and then you have a certain amount of kinetic energy at the end, the difference between those is the amount of work that you have done. Power. What is power? Power, we know that I've just told you that force times distance is work. The unit of work is the joule, which is a Newton meter. Work per time is power. So power is work per time, and we use the watt for that. You might say, how many kilowatts does this house use a month? Believe me, it's not pretty. Okay, so work is force times distance. Power is work per time. So we get to the final crash review of first semester AP Physics, momentum and impulse. So momentum, P equals mv. The momentum equals the mass times the velocity. I once ran into a wall because I was playing basketball and the floor was pretty frictionless. And so my velocity, which was great, times my mass, which was great, hit the wall and broke my elbow. So momentum equals mass times velocity. momentum is conserved. So if two things hit each other, the m1 v1 the m1 v1 plus m2 v2 after the collision is going to be the same. The total momentum is going to be the same, even though some of the momentum may be transferred from one object to another. Or if the two objects stick together and continue, then you're going to have a combined mass times the end velocity that will equal the individual masses times velocity before the crash. So m1 v1 equals m2 v2. I didn't do that quite right. m1 v1 plus m2 v2 equals whatever m1 v1 plus m2 v2 is afterwards. Okay, kinetic energy and momentum. So impulse is force times time, and this equals the mass times the change in velocity. So F delta t equals m delta v. F delta t equals m delta v. This will come in handy with certain problems that they give you on the AP exam. Okay, and this is review. Work equals force times the distance, which is 1/2 mv squared. Okay, types of collisions. We're now coming to the end. There are elastic collisions where no mechanical energy is lost. Kinetic energy of the system remains the same, but there are also inelastic collisions. This is where momentum is conserved, but there is some loss of kinetic energy. So, in sum, what have we been doing? Here's what we've been doing. On the first day of Christmas, my true love gave to me 5 velocity equations, 3 of Newton's laws, 2 for circular motion, kinetic and potential energy, conservation of energy, work and power, momentum and impulse, and another whole semester yet to go.